Okay, let me thank the organizers for the invitation, and especially for nice weather, at least for these few days, which allows escaping from the heat of New York. Okay, so this work started with my student Adam Alkadi, who unfortunately passed away. Okay, so it has the subtitle, Composite Order Parameter in Neutral Multi-Component Superfluid Induced by Thermal Fluctuations. And I believe this idea first came from Yegor, more than 20 years ago. And I'm talking about the excitons, indirect excitons. There is a long search for the condensate of excitons, and first people talked about excitons directly interacting with light, famous paper Moskalenko, Snow, and long time ago. But right now the interest shifted to the so-called dark excitons. So excitons formed between, let's say, gamma point of the valence band and some valley separated from the gamma point by large momentum, so that there is no direct transition, optical transition, which tells us that these excitons can live two factors longer than bright excitons. Another interesting thing, which I believe people didn't pay attention enough, is that I'm talking about the materials characterized by D3 or C6 symmetry if you ignore magnetic interactions, like in transition metals, the halcogenides. So what happens now that with hexagonal symmetry you have at least 6 values for the momenta. It means that if you have the condensation of dark excitons, there should be at least 6 components of the order parameter corresponding to each value. If you consider, let's say, twisting couple of layers, you can get to 12 correspondingly, and so on. If 3 layers, 18, and so on for the values. How to describe these values? Let's say you can assign order parameter to each component, characterized by the Valley momentum, which is large, right? And the amplitude, which is the long wave amplitude, and supposedly it can condense. And then the order is characterized by the effective phase of each value. What is interesting about these systems is that there is no standard Josephson effect between each value because of this factor. So basically this minimal Josephson parameter is washed out due to the highly oscillating cosine coming from this factor. However, you can have the higher order Josephson coupling between time-reversed pairs of time-reversed values. So bar means, let's say, let me go back. Let's say this is the value and this is its times-reversed replica. So their momenta is opposite. Similarly for these 3 values, or 12 or 18. So then the product of these two operators, basically the Q oscillation doesn't happen in this product and correspondingly in this product. So pairs of excitons from the time reversed valleys can transform into pairs into another valley. So how to describe this system?
But also presumably you are in a lattice, or?
Yeah, the simulations, well, it's a material characterized by the symmetry, but the simulations were done on some kind of elementary lattice here, not related to the symmetry, hexagonal symmetry. So the only thing which comes from the symmetry of the original lattice is the number of the components.
I see. So the difference between Q nu and Q mu cannot be absorbed by the lattice? The lattice weight that there's too much?
No, these are not, no. This is somewhere in the middle of the
Zone, okay, yeah.
of the inverse lattice. Yeah, so basically what is the elementary model which can describe it? It's XY model corresponding to each component, right? The summation of the components, and the lattice gradient describes the phases on nearest sides. And this is the higher, let's say, second order Josephson coupling term. So this is the minimal model which we looked at.
And what's A?
Pardon me?
What's A?
Oh, yeah. A is the effective, it's a constant vector potential introduced by the, if you describe within each valley, there is a shift of the quasi-momentum, and it corresponds to, let's say, Q, corresponding to the Q. But it's a constant. It's a constant. It's not the actual magnetic field because system is neutral. It's simply shift, Galilean shift of the system.
And what is the space dimensionality?
I will talk about 2 and 3 dimensions. The results are different, unexpectedly different.
That's right, but isn't A the same as the difference between the two Qs?
No, it's a Q. Roughly speaking,
Yes,
it's a Q. Yeah. So let's do some primitive analysis, if you wish, mean field analysis of the system. In the limit when the Josephson coupling is very large, so basically let's fix this cosine to unity, so the difference of these phases is 0, then you can introduce, so to say, total phase and the phase difference between valleys, right? If you substitute this, automatically it will be satisfied. But then you consider 2 other parameters, let's say, total order parameter, if you wish, paired, and the subtractive order parameter, let's say. In Yegor classification, it was charge order parameter, and this is like neutral order parameter. Then if you substitute into the gradient terms, you will immediately see that the effect, and ignore higher order, so you do the expansion, Gaussian approximation, you will immediately see that the effective stiffness of the charged order parameter is multiplied by the number of the components. And the difference, of course, is not, and there are the remaining reduced by 2 differences of phases. Then it's natural to expect that if n is large enough, this order parameter will dominate. So roughly speaking, there is a okay, so in this range, yes, in this range, basically you can have this phase condensed while this phase is not condensed, at least for n bigger than 2. And then you can literally create a phase diagram, something like that, so that if here it's a temperature, it's a classical system, so this parameter can be viewed as an inverse temperature, just one parameter t. So you get the phase diagram. For large temperature, of course, you have normal phase. If you reduce the temperature, you go into the paired phase, charged paired phase, and then eventually you get into the n-component superfluid where everything is condensed. All right, but then if you consider the whole
How
thing,
come that A's disappear? Where are A's?
okay, so A disappears from phi because it's opposite, they summed up.
Okay.
A stays here, but it's
But this term is irrelevant.
it's irrelevant. Yeah. But if you don't do the Gaussian approximation, but simply sum up cosines, what you will see that the total phase and the difference of phases come as one expression. So then you would say, okay, if this is disordered, how this can be ordered? In the Gaussian approximation looks fine, but with the full xy terms, which restore compactness of the phases, you will say, this is nonsense, this cannot happen. Okay, this is the controversy. This is the controversy. Well, to some extent, this is what we do when we analyze system within some mean field approximation, elementary fluctuations like one loop approximation, and happy with the results. But what this system tells us that actually this result should be taken with the grain of doubt, okay, and should be checked by simulations. We will see that some truth does exist in this system, only partially. Okay, the line is not really straight, and furthermore, in 3 dimensions, there is no paired phase at all. It can exist only in 2 dimensions. Oops, it jumps. Yeah. So the simulations were done using so-called duality. Let me say a few words about that. So let's say if you have elementary XY model, it can be transformed into its dual representation. So I'm talking if you try to calculate the partition function in terms of the phases, it can equally be done in the representation of the link currents, integer link currents, satisfying the Kirchhoff rule of currents on the links. And so instead of the side phases on the lattice, you have link currents, which form closed loops. And the superfluid stiffness is characterized by the winding of these loops. So let's say in the, it should be square here. Okay. Windings of these loops, so that in the superfluid phase, loops proliferate and create macroscopic windings. Square. Okay. So it's a positive. And in the normal phase, loops are short like that and no windings exist. So this is a very convenient representation for the numerical simulations. So I'll be using this representation, this idea introduced by Villain for the model which I, yeah. So now we have n components corresponding to each value, and we have this Josephson term, and essentially doing the same procedure, this model can be converted into, it's a partition function, in the partition function, to the effective Hamiltonian, which is like dual Hamiltonian. And the term coming from the effective vector potential. So the Hamiltonian consists of two terms. First is the same J currents I just mentioned before, plus some constants, side constants, satisfying the following conditions. So J currents now are not conserved, individual J currents. So link currents can come into the site and transform, but they transform in pairs. Let's say if current of the component nu and its a time reversed replica come to the site, they can transform into another currents with index mu, let's say different index, which come out of this site. So in order to illustrate this, this is the example of the configurations, typical configurations. So different colors indicate different components, and dashed lines correspond to the time reversed replicas. So let's say circles show us the sites where this transformation happens. Let's say two currents, green currents, and time reversed come to the site, and they transform into two blue currents coming out of the site. And of course, you can have one sort of current which forms closed loop without any transformation. So just one current cannot transform. Only two currents must be transformed. So in this system, you can introduce corresponding stiffnesses. Stiffness corresponding to the charged currents are determined by the total winding of all phases, and the difference stiffness corresponding to each index nu consists of the difference between windings in each component nu and its time reversed replica in each direction. So how to distinguish these phases? So in the standard superfluid n component superfluid phase, each windings are uncorrelated, so independent essentially, and it means that the total of this charged stiffness should be the same as the total of the difference of stiffnesses. Yeah. And so let me now demonstrate the results of simulations using the two-worm algorithm, modification of the worm algorithm introduced by Nikolai and Boris a long time ago, and modified for the case of two-worm algorithms a bit later. So, but you may say, okay, each worm corresponds to each component, but now we have more than two components. Should we use, let's say, 6 or 12 worm algorithm? No, basically it's enough to recreate the whole configurations by two worms. Let's say worm corresponds to calculating the correlator. So we each time when two worms are opened, it's a 4-point correlator between two different components, and basically shifting between pairs of components is enough to reproduce all the configurations. And yeah. So first, let me show the result for 3 dimensions. So this is a clear signature of the first order phase transition. So this is the temperature, and so this is for N6, I believe, yeah. So for low temperature you have, so blue and red corresponds to the charged stiffness, and red to the difference of stiffness, and they coincide here, which clear signature of the n-component condensate, no paired correlations. And then simply system drops by first order phase transition into normal phase, and with pretty strong hysteresis. Okay. So now in 2 dimensions. So here we see 2 cases with slightly different temperature. Let's say at low temperature we have the dependence of the stiffnesses. This is the charged stiffness, and this is the difference of stiffness as a function of the system size. And we see that they're slightly different, but eventually they saturate to constant value independent of the size. And this is NSF phase, n-component superfluid. But if you increase temperature a little bit, what you see, the flow of the total stiffness saturates as a function of the system size, and the difference essentially exponentially falls to 0. And this is the phase diagram. So what is interesting here, topologically it's similar to the diagram obtained by the elementary analysis. What is different is that there is no paired phase for the 4 components. It starts for 6 components only. So here you have temperature, and here you have number of the components. System has just one parameter, temperature. So the analysis was done in the limit of very large Josephson coupling, so which becomes irrelevant. And this is the, of course, values in between makes no sense, so it's just, of course, only discrete number of the components. So this is the NSF phase, and the saturation of the stiffness, the boundary corresponds to the jump of the universal jump, standard universal jump of the Beckett type, and the upper part corresponds to the non-universal jump, which is 4 times higher. I will explain why.
So PSF is the phase where only the composite order is.
Yes, paired superfluid. Paired superfluid. Yeah, so how the universal jump was analyzed, basically using the RG, Beckett RG, and this is the Beckett separatrix corresponding to the transition. It's a function of the system size, and basically fitting the data for finite size as best as possible. You can determine the universal jump for the charged order parameter and for the difference order parameter, and lines corresponds to 8 over pi and 2 over pi. Okay. Yeah, now why paired phase exists. So it's not easy to see in the original direct representation, but in dual representation it has a very clear picture. Let's say you have a loop consisting of time reversed currents, J currents, and they transform, let's say red into pairs of green, and so on, a closed loop. So this system represents in some way as a DNA with complementary bases. So the number of pairs is NV over 2. And what will happen if you, let's say, swap these pairs over the loop, you gain additional entropy. So you expect this loop to proliferate. Normally, these loops proliferate because of the shape fluctuations, but now in addition you have this DNA type swaps of the bases, and it generates additional entropy. So if you write down the free energy of such a loop, you will get energy due to its length, right? So which is positive. But then there is an entropy due to swapping of these pairs, which gives you negative sign here, and logarithm. So basically the boundary by where the free energy becomes negative, this is like Beckett types argument, develops sort of logarithmical dependence on the number of the components, while the previous analysis was telling us that it should be linear, proportional. And when such a loop proliferates, it corresponds to the finite stiffness, or charge stiffness, and I'll give the argument that this type of loop doesn't want to proliferate. Okay.
And can you tell us what is the universality class of this transition?
Beckett. Березинский-Косарев ставлюсь. But I will say, okay.
Sorry, the upper one or the lower one?
Both.
Both are.
Yeah, but why the universal jump for the upper one is 4 times bigger? Because we have loops carrying double currents. So lower one corresponds to the proliferation of a single loop. But now the charge carried by these loops is double. It means winding squared will be 4 times bigger.
So I missed a little bit. If I look at the superfluid phase, is the superfluid phase involve some superposition of all, let's say, 6 order parameters, or is just one?
Yeah,
is it
it's a
collinear
superposition.
state, or is it a crystalline state?
It's a superposition of all parameters. And what's interesting, since they take coherence from the opposite, from time reversed replicas, it means that the order is characterized by 0 total momentum. So each valley condenses, let's say, at large momentum, but due to the correlations between pairs with opposite momentum, the resulting order is at total momentum 0.
No, I'm talking about superfluid one.
It's superfluid one. Yeah. Oh, you mean n-component superfluid?
Yeah, n-component superfluid. Is it it could be just a plane wave, but one of the 6 plane waves, or is it a hexagonal lattice?
Yes, since it's a symmetric, I would say there are phases. Each phase, there is a phase condensed in each component, and there is no coupling between phases except for the higher order Josephson. Whatever this difference of phases are independent variables. It could be just one component, but it will be kind of
The condensate
there is a
one of the
there is a
6
degeneracy, I would say, degeneracy. But this state is not degenerate.
Okay.
Yeah, now the argument why the counterflow phase cannot happen in this system. So let's say assume this order parameter is 0, but the difference, which is counterflow, condenses. Well, in this case, you expect to proliferate loops with opposite orientations. Let's say 2 components with opposite flows come to the site and transform into its time reversed replicas. And now, in order to close the loop, you cannot get other components. Only following this rule, you have to keep the same component. So there is no additional entropy gain due to swapping of the components. Yeah, but in principle, you can have counterflow with, I would say, tetrabound counterflows. Let's say when charged loop which gains the entropy in one direction, and the opposite loop of one component in opposite direction, then such a state with counterflows of higher order, tetrabound, can occur. Well, let me skip the detection of the, the key question to answer is, what happens if we take into account quantum fluctuations? Since we know that, let's say, two-dimensional system at T0 corresponds to 2 + 1 dimension, then in it will be three-dimensional system. Essentially, the transition must be first order. So at some point, if temperature goes up, what to expect? Should we expect that first order transforms into the second order? So this is kind of possible phase diagram. So if as a function of temperature, if you consider quantum mechanical, there should be first order phase transition, no paired phase, and eventually paired phase appears somewhere at finite temperature. Okay, but no simulations were done, and I would say this is the question to answer. Yeah, I'm done. Okay, thank you.
We have time for some questions?